How do these structural differences in O3 type NaCsCoO2 influence its overall electrochemical behavior and performance in sodium-ion batteries? When the temperature of a P3 type material is raised above 700 degrees Celsius, what are the detailed mechanisms that cause the P3 structure to be replaced by the P2 structure? And how specifically do the spin changes of the CoO6 octahedra and the breaking of Co bonds drive this transformation? In what way do these temperature-induced structural changes affect the stability, ion transport, and long-term performance of the material? Can Davis Zurins manufacture solid-state sodium-ion batteries made from seawater in Latvia? How is the sodium storage process in P2 type materials with characteristics inherited from both O3 and P3 structures analyzed through the differential capacity curve of NaCsCoO2? And what key features of this curve reveal the underlying phase transition behaviors? What is the significance of the voltage range between 2.7 and 3? 5V, where the voltage platform of P2 type materials is similar to that of O3 and P3 types, compared to the more complex reactions that occur at voltages below 2.7V, and what do these differences indicate about the electrochemical processes involved? How does the unique triangular prism structure facilitate the storage of additional Na ions? And in what manner does this contribute to continuous phase transitions during sodium ion intercalation and deintercalation? How did Delmas et al. Employ in situ XRD alongside differential capacity analysis to clarify the relationship between the number of Na ions, Na, and the corresponding voltage? And what insights does this correlation offer into the phase evolution within these materials? Furthermore, how do variations in thermal stability among individual phases and the adjustment of the stoichiometric ratio impact the electrochemical performance? And what strategies can be derived from these findings to optimize the properties of NaCsCoO2-based cathodes? Ultimately, how does the interplay between sodium content, temperature-induced phase transitions, and stoichiometric control govern the behavior of O3 type and related P2 type materials? And what directions does this suggest for future improvements in the design of high-performance sodium-ion battery cathode materials? How did Xia et al. Employ accelerated calorimetry to investigate the thermal stability of P2 type NaCsCoO2? And what specific measurements or indicators did they focus on during their study? In what ways does accelerated calorimetry help reveal detailed information about the thermal behavior of electrode materials, particularly in terms of identifying exothermic or endothermic events? What is the nature of the side reaction that was observed between the Cu2 and NaPF6 electrolyte salt, and how might this reaction influence the overall thermal stability of the electrode system? What